Okay. So today we continue our discussion concerning contours. As usual, we will cover this material only through examples with illustrations, how each virtual instrument works, its implementation areas, and most interesting specifications. I shall begin our work with example number 21, with which we discussed how to find the areas of a contour. As I remember, it was named, it has the number 21. 21. This is the virtual instrument I am going to talk about now, and then we will move forward. Showing you back again the block diagram, as you see, and reminding you with the basics. As you see, we have read an image by using the file path, and in this case, we are going to use the dimensions of the image. The X resolution and Y resolution are extracted here and taken as inputs, as you see, to this cluster. This cluster is realized by using the bundle function. As you know, every rectangle could be described by 2 points, the upper left point and the lower right point. The upper left has a coordinates of X and Y, and the lower one has also another coordinates X and Y. If the rectangle is going to be rotated, so we need to introduce the fifth parameter here. Here, as you see, I am giving the value of 0 for rotation angle, which means the angle will be vertical or the rectangle will be vertical or horizontal. The image now will be surrounded by this external rectangle. It is called sometimes bounding rectangle. The upper left point, X is equal to 0, is taken equal to 0, and Y equal to 0. And the lower XY are the dimensions of the image. So, as a result of this assumption, we conclude that the whole image now is enclosed within the bounding rectangle. After that, now we use this rectangle to create a descriptor for it, for the region of interest here, which is the rectangle, and feed it to the IMAQ extract contour. Of course, IMAQ extract contour requires the image itself, which we have acquired also, and if required, to manage or select the appropriate way of searching the image from left to right or right to left, up and down, and so on, when the image is, when the surrounding or bounding rectangle is used, or when an anomalous shape is used also. What is interesting and why I am repeating this, because in the previous lecture I told you that in this part here, this is a sub-VI added in order to calculate the area of the enclosed image, the image which is enclosed by the contour. And we found at that time the area. I wanted now to tell you that instead of using this somehow complicated sub-VI, we can use an IMAQ polygon area function, which can carry out the same task without drawing this complex sub-VI. This function here is included in IMAQ, as you see. When you go to machine vision, sorry, I want to go to machine vision here, and I think we go to analytic geometry. Here you find IMAQ polygon area. As you see, there are a lot of points which describe the coordinates of specific vertices of the shape. Now, if we want to know a little bit about this function, we go to the help and see here that this function computes the area of a polygon described by the coordinates of its vertices. So what you need is to give the coordinates of these points, and then the area will be calculated directly. But now, when having the contour, practically, we can, or we have already achieved the coordinates of these vertices. So what do we need is to take this array of clusters and feed it to the input of the IMAQ polygon area, and we will get directly the area. When I run the program, here, as you see, the arrow is braked because I have put the shape here and I didn't cancel it. Now the program is okay. When I go to the front panel and run the program, I have found that the area was equal to 54,104 pixels when using the sub-VI, and it is equal to 54,104.35 pixels when I used the suggested vertices coordinates. Comparison between both values shows you that we have exactly the same answer. So, of course, now, if there is no need to use this sub-VI, of course, you are advised to use this polygon function to get this coincidence and very perfect answer. So again, the vertices which are required and introduced are practically these points, the contour points, which are describing the contour of the whole image which we are interested in. I hope that is clear now. We will work on this a little bit also with some detail in the coming examples. But for now, let us move to the next example. Let us move to example number 21-1. If there is something added, I have to explain to you. I think I have explained some details also of interest use for this function. Let us look at the block diagram and then we can guess. Okay. So we are talking about the same idea and the same example, but I have done some modifications. At first, I disconnected the cluster which feeded the information regarding the region of interest here, the descriptor. It was connected by this cluster here. I disconnected it, and now the coordinates of the original image are not used. Why? Because I am interested now with another image or with part of the image. Indeed, what I am interested in is really to find the area of this circle, or the area of this circle, or the area of this circle. The coordinates of the points at the edges here are obtained by the contour function. I know these coordinates. I can make the region of interest to be enclosed within a rectangle which surrounds either this circle or this circle or the other circle, and then accordingly I will get the coordinates of all the points of the contour, and these coordinates will be the coordinates of the vertices of the polygon shape, and then I can find the area of this circle or this circle or this circle. This is the idea. So for that, I have suggested to use IMAQ construct region of interest and to define the type of the surrounding or bounding area to be a polygon. It could be, as you see, an oval or rectangle or an annulus. You know that. I have explained that before. I have selected it to be as a polygon, for example. When using this function, you remember this function exists in the IMAQ functions, and when we use it, we define the polygon or we define the rectangle or any region of interest. We define it on an external image which is displayed externally and not inside the front panel. So what do we need here? We have defined the tool. Here is the tool which we are going to use, the polygon, and the image at the input, which is the acquired image, the complete image. And now we will be interested in part of this image defined by this polygon. And this will be, of course, will surround any of the circles which I have shown you. The output cluster here is fed to unbundle by name function to get the global rectangle value. And this global rectangle value here, as you see, it is an array. I have converted it to a cluster because this function requires a cluster. And the number of elements here must be 5 as they were here. 1, 2, 3, 4, and the fifth one, although it is 0, but it is one of the elements of the cluster. So this cluster size is 5, is made 5. How to do that? I right-click it and select cluster size, and I have already written 5 there, and okay. So now there is a match between the dimension of this cluster and the input of IMAQ convert rectangle to region of interest. And now this region of interest is fed to the IMAQ extract contour. And the output now of this IMAQ extract contour will be an array of clusters. And this array of clusters now, as you see, this is the array of clusters. Here, look, 2 brackets means an array, and these small squares represent a variety, a number of different data values included, and this array of clusters is fed to the IMAQ polygon area. Here is an indicator which gives you the value of the area of interest here. Okay. Now, some results regarding this investigation. So global, let me summarize it for you. The global rectangle is defined by selecting the tool of IMAQ construct region of interest. Here, I have selected polygon. When rectangle tool was selected, the area calculated was the area of the small circle, of this circle, the upper one and the lower one. Both of them were investigated. It was 54,119 pixels. And the area defined by using IMAQ polygon area was 54,294 pixels. So if you subtract the smaller from the higher one and refer the difference to the higher one, you get a relative error value which is equal about 0.3 pixel, which is very small value and negligible and cannot be taken in consideration. Exactly, we got the same results by using the IMAQ polygon or by using this sub-VI. Yes, when the polygon tool was selected instead of the rectangle, we also got the same answers, 54,119 and 54,310, and the error was about, as you see, 0.33 pixel, which is the same, which means there is no difference at all. The most important here is to enclose the area of interest with the bounding tool, and then you will get what you expect. The other note, if we reconnect the bundle by name cluster again, here, we connect it here, and now we disconnect this part, and selected the coordinates. Which coordinates? This is 1, 2, 3, 4. The upper left X and Y values, and the lower right X and Y values, which are here. With these values, how I guessed these values, I went to the image there in order to surround this by a rectangle. I have found this point, for example, here, the upper left value, the lower left value, to define the rectangle, which is going to enclose it, to surround it. And so these values were defined approximately in order to enclose the upper small circle to find its area. The program to area results, the results of area found by IMAQ polygon area or by the sub VI for the small circle of the above were 1033 and 1033.7, which are practically the same. In order to verify both results, the circle radius by using eyesight was estimated to 18 pixels. And by looking at it by myself and estimating the position of the center of the circle, I found that the radius was about 18 pixels, approximately. Now, if you square the radius and multiply it by p, 3.14, I'm sorry. This should be 3.14. It will give you the area equal 1020. This is by calculation and estimation. And by measurements, it was 1033, as you see there. So the difference I am here illustrating, the difference is due to radius estimation error, which has done by my eyes. Concerning the lower, of course, if there is a need to have a better accuracy of estimation, I can find exactly the position and the coordinates of the circle. Concerning the lower circle, the results were 1030 and 1026, which are also very close to each other. Well, I hope that when looking at this example and investigating every part of it and what I have discussed with you, I think that you will find it very useful in your life. So we finish with this example and move to another one. The next example will be 21.2. Here it is. Okay. What is this example about? Let us look at the block diagram to remember what is going on. Okay. So what we are using here, as you see, this is a sequence structure where at first in this part, we implement it firstly, and when it is implemented, the other part sequentially will be carried out or implemented. When implementing the first part of it, we get the template of the part of the image which we are interested in. And in the second part here, the template is now used to define the matching between this template and the other elements of the image which are considered as a repetition for it. Another way, we need to find the number of matches. To realize this interesting program here, we need to use two also interesting functions. The first one, IMAQ learn pattern. It has a number 6 with IMAQ. IMAQ learn pattern 6. And the other one is IMAQ match. IMAQ match pattern number 4. Where they are, I can show you now. Let us go back a little. Find patterns here. If you open it, you find IMAQ find pattern 4. This is an algorithm, a complex algorithm, of course, taken from machine learning and is used to find the number of matching of components existing in the image. The other one, which is used to learn the patterns, I think it should be here. If we open it, yes, here, IMAQ learn pattern 6. Of course, you need to know about each of them a little bit. For this example, for this one, for example, if you go to the here, we see that it creates this function, or the learn function, it creates a description of the template image you want to search for. So at the output here, you, of course, at the input, you give the image or part of the image which you are interested in. And at the output, you will get a template report and also another the image or the extracted image part which of interest. Well, this template image output is fed now to the other function which matches between this template and between the whole picture, the whole image. So I want to detail this also to you. First of all, I have to cancel this so that not to disturb our work. So we have an image in a file and we have read the image here. We fed it to a function IMAQ clear overlay. If there is an overlay from the previous stage, we do not need it. We cancel any overlay and we have now a pure image which fits, as you see, the IMAQ construct region of interest. Here we have decided to select the tool as a rectangle, and the output descriptor, as you see, is fed to the function. Let me fix it for you and bundle by name. And we get here an array as usual. This is the array which represents the 4 coordinates of the rectangle. This function is IMAQ extract function, which requires, in addition to the bounding rectangle, it needs the input image. This is just a memory location to put the image in. So at the output here, we have the extracted part of the whole image. And now this is fed to the IMAQ learn pattern function. This, as I told you, a comparatively complex machine learning function, and it gives the output as a template report or also the image of the template itself. We shall use the image of the template itself, as you see, and feed it to the second stage. So after having this template, we feed it to the IMAQ match function here. Here, as you see, in addition to the original image itself, without any overlays. And now this function computes the whole work and gives the number of matches which exist between the reference template and the other elements of the graph which repeat the same template. This function really is used to overlay the matching part on this whole, on the original image. Now I'll go back to the front panel and try to illustrate to you what I mean for that. So what do we have? Here is the original image. This bracket, a battery bracket. You remember the battery has these brackets which are tighted around the battery. And it has these holes for the bolts also. So the idea is to create a template for one of these holes, and then to ask the IMAQ pattern function how many holes we have in the original hole image. We shall do such examples also in future. So first of all, I have surrounded one of these circuits with a rectangle. This is the region of interest, which was fed to the learning part. And at the end of that, we have got here an image which represents the template. This is the template now. And now this template is used in the other part of the program to define the number of elements here, which are considered as images for this template. We have found them here as 2, and these 2 are also shown surrounded by rectangles for the user to know them. Here you are supposed to introduce some parameters for the matching function, which some of them, which is the number of matches you request, you expect. Here I put 2. I can put 3, of course, but I shall get 2 instead of 3, anyhow. And the maximum match score here. Why it is a score? It has a score, of course, because this is an approximation machine learning algorithm. The complete score will be 1000. If you increase the percentage here, suppose instead of 750, you put 950, maybe you may get only 1. You guess the computer or the program will guess only 1 circle, because it is a very tight requirement. And if you make it less, you get sometimes errors. So it depends. You have normally we use 700, 800, 850 is good numbers, good practical numbers to have an accurate results. So when I run the program now with this data, here I have put 3. Okay, the number of matches which I have got before are 2, and here are shown, they are 2. But now if I run the program, as you see here, now the region of interest is not shown. I have to show the region of interest as a rectangle, so I enclose it like this, and I say okay for it. Now I have a template already created. After the creation of this template, the IMAQ match function has found 2 matches, although I have requested 3 because there is only 2. Suppose I want 1, I think it will give me only 1. If I expect 1, let me run it again. And let me enclose the lower 1 for you. And I say okay. And now it is created. And now he got 1 upon my request. It doesn't show me 2. If I increase it to 2, it will show U2. Now, okay, 2. Okay, now I think you guess the importance of such an example in real life, because many times you are required to calculate a number of elements, especially in assembling, for example, stations. Suppose you are supposed there to, or the robot is supposed to fix or to bolt 100 bolts of a given type, and there's sometimes an error which takes place. So by carrying out such an example, by giving the photo of the original working place and the template of that bolt, you can guess that the robot has already fixed or bolted 100 bolts or 95 bolts with some error or so on. Of course, other examples in life in implementation are numerous, and of course, don't save, I don't want to save a new thing. Okay, now this is 21.2. Let us go and to 21.3. Clearly, 21.3 is not that different from 21.2, but it is interesting from a practical point of view. I have just also selected for you an image with different elements, as you see, separated elements, not as parts in the previous one. And I have selected or made a template for this screw, for example, and then I asked the IMAQ match function to tell me how many elements in the basic configuration I have. So if I run it, this is the image which appears. For example, I surround this by a rectangle. This is the region of interest for me. Okay. Now here I shall have the template. And now we have here two squares which represent the matching. Let us go back again and run it and seek, for example, for this wheel or frame, and consider this is our region of interest. Okay. Now we shall have another template here. And if we consider the match, here we have here one matching, here's the other matching. So we have two matches in the original case. So this is just also demonstration for you, but also it is a good example. Okay, let us go to example number 22. 22. Okay, we are still working with contours. Really, I have made a summary for you to be read by you slowly concerning contour analysis. I only just want to remind you with the basic idea about it, that contour analysis generally is used to detect defects in objects by analyzing their contours. reminding you by the basic thing here, which is that boundary curves of objects are connected to produce contours. The contour is a boundary curve, a sum of different boundary curves. And with this, we have to conclude that there should be very clear boundary edges which are distinguished clearly from the background. And also reminding you with the basic thing that boundary curves are generally a set of edge points. Now we know what is the edge and edge points, and collection of edge points gives you a curve, and this connection between these curves gives you the whole contours. This is the basic of the contour, and as you see, because we refer here to edges and finding edge points and boundary curves, so practically the image must be grayscaled. We cannot do this work directly with the color image. The other important thing here is when working with analysis or using the contours to analyze the defects or the existence of the defects, here we know we need to compare between two contours or between a reference contour and other contours which could be real ones and could have some defect in them. And for this, we need to find the deviation, the departure between the coordinates of the image, of the contour of the image which is taken as a reference, and the contour of the other images, which is the product which we are interested in. This difference is called the distance between contours. And also, by using IMAQ, this distance could be found for every coordinate point in the contour, which is very marvelous. So let us go and explain with you also with some detail around this thing. First of all, here I am showing you an image, which is in black, as you see, with a red line surrounding it, which is the contour. This contour is calculated by the contour function. As you see, it is a closed contour. Here, we have a separate image of the contour itself only. And here we have another image with the contour points to illustrate for you how the reality is and how we can manage the size of these points to increase them or to decrease them upon request. Here we have a simple graph which represents the curvature profile. We mean by that the change which takes place in the values, really in the rate of change of the values, the differential change of the values of the points of the curvature. If the departure here is, as you see, a very small pulses as shown here, which is around 0, this means there is no serious problems with the contour. But if the departure here is going as a spike high, more than 1, or this is 1 and 2 are reference values. So if it is higher than the reference threshold value, this means that there is a defect and this must be considered. If we go to the block diagram again here and consider what do we have. So this is the basic program, which is down here. I am surrounding it. As an input, as you see, I have a cluster with 5 elements, which represents the coordinates of a rectangle. As I told you, 0 is given here to show that this rectangle is vertical or horizontal, but it is not inclined by any angle. And now, as you see, I am using the IMAQ convert rectangle to region of interest, and this is the descriptor which feeds the IMAQ extract contour function. And this is the image which we have read from a given file. This is, before, nothing new. At the output of the contour function, as you see here, this is the information which we have, which is the contour points. Here they are. This is, as you see, an array. And each element of this array is a cluster. And each cluster consists of 2 elements, X and Y, X and Y. So every cluster represents a point in the contour here. And there is a number of this of points, which could be 1,000, 2,000. This is also could be achieved by the program to know the number of them, total number of them. For curve extraction, this curve extraction, you need, first of all, to be sure that the edging threshold is appropriate. It is suggested to be 75, but of course you can manage it by increasing it a little bit or decreasing to have the best contrast as you want. The edge filter size here could be normal and could be for contour tracing. Preferably, in this case, we need it to be in a contour tracing. Concerning the contour points, which are here we see as a curve, we do not see the points, but you can increase the width of the red line, which represents the increase of the points, the diameter of the points if they are taken as filled circles. And here normally we want to overlay this contour around the original image. Now, if we run the program, as you see, we have got the contour points beginning from 0 up to the last one. And the red, as you see, represents the contour. If we change this color, okay, let me stop it. And if we change this color, for example, to green, and we run the program, now we will have, as you see, a green curvature which represents the contour itself. Concerning the width, it is given 1, but we can increase the width. You can follow me on the picture and see how it becomes thicker and thicker upon request as required. This is interesting. Now, if you go here, this is the 0. This data, if we want to go to 0.1, we will get another value, 2, 3, 4, and so on. So it depends. Now, if we go, let me stop it and go back to the block diagram and show you what do we have here. Here is just an addition. I made it for you to show you that we can change the color or we can change the size of the points of the coordinates of the contour by another means. This is sometimes required, especially if you have another contour which is not realized by using IMAQ extract contour. For that, we need to connect the output of the contour, which is the array of clusters, to the input here. I have to cancel this cluster. This is 0, 0, not needed. Okay, and now I have to connect it with the contours points, and the image here must be connected with the original image. And now if the color was there green, as I remember, let us put the color here red. And now we go back and run the program. Here it was green. Now if we run the program, let me stop it. It becomes green, sorry, red, according to the red. And the interesting thing here is that I can manage again the thickness or the let me say, first of all, I can change the shape of each point. Instead of having a point or a filled circle, I can use a circle which is not filled, and I can use a rectangle for that. Let us try to stop it and go back and try to do something here. Maybe here the frame, it is taken as a frame, not filled frame, which is okay. So, which is okay here. Let me try to change the size here. It is taken dot 2, dot 2, minus 1, minus 1. This is the values, as you see, which represent 2 points. If you make the coordinates of one point in negative and the other ones when positive, so the difference between them becomes higher. So let me take this one to be dot 5, for example. And this one will be the same, 0.5. And now if I run the program, let us go back and see how much it will be. Okay, it doesn't seem to me that it changed a little bit clear. So let me make it higher value, 0.9, for example, 0.9, for example. And when I go back, I run it. It is, of course, thicker than was before. This one must not be increased at the same time with that one. And now, stop it. As you see, it is smaller. Doesn't seem very effective. Stop it back. I go back. It seems to me everything is normal here. I don't need this element here. And there it is. Let me have it 2. And here it have it to be clear only. And now, if we go back, it is clear. And the effect is seen, as you see. Okay, so when we go back now to the front panel, we are at the front panel, we don't need anything else. So at the output here, okay, I need to go to the front back to told you about the curvature. Here we have a function which is called IMAQ compute curvature. It is fed only, as you see, by the output image of the contour. And this input here represents the size of a kernel, which is considered as a filter here to the image. And here we get the curvature. This curvature is just an indication to you to which degree the points are close to each other and there is no serious spikes or spike values happening. Yeah. And this element only realizes a time delay to the while loop which we have here. So I think now you know a little better what is the IMAQ extract contour function, how to manipulate it, and how to use it, and what is kept not discussed with you is how to use two contours together to compare them and to find the distance between both and the error if there is an error or defection. Anyhow, this will be discussed in the coming future. Until then, I wish you a happy day and goodbye.